Do not let the media mislead you into thinking a robot is merely a walking battery. In reality, Optimus is a continuously vibrating electromechanical system where the power source endures the harshest physical punishment. Solid-state batteries prone to abrupt catastrophic failure and costing an exorbitant $600 to $800 per kilowatt-hours simply lack the ruggedness to survive this environment. By industrial reliability standards, such fragility is simply unacceptable. Let us begin with the most obvious limitation that is consistently ignored: vibration. Have you ever wondered why suspension bridges are not built from glass? Because rigidity is the enemy of dynamic stress. Modern solid-state batteries rely on ceramic or sulfide-based electrolytes. These materials are extremely dense and offer excellent ionic conductivity in controlled, static laboratory environments under compression. Mechanically, however, they are unforgiving. Their Young's modulus typically ranges from 20 to 30 gigapascals, comparable to concrete. Now place that material inside Tesla Optimus. Optimus is not a benign electrical system. It is a high-frequency vibration chamber. Every time its metal foot strikes a factory floor, it generates impact forces in the range of 1.5 to 2.0 times Earth's gravitational acceleration. These shock waves propagate directly through the kinematic chain and into the battery enclosure. In a conventional lithium-ion 4680 cell, the liquid electrolyte behaves like a hydraulic cushion. It has effectively zero shear strength. When the cell vibrates, or when electrodes expand during cycling, the liquid simply flows to maintain contact. The system is mechanically self-healing. Now ask what happens when that same vibrational energy is applied to a rigid ceramic interface. You get interfacial delamination. Without sustained external pressure, often exceeding 5 megapascals, solid electrolytes separate from the anode and cathode. The moment physical contact is compromised, the ionic pathway collapses. Empirical vibration testing data from 2025 shows that when active contact area in a solid-state cell is reduced by as little as 5%, internal resistance can spike by over 40%. Ask yourself honestly, would you strap a porcelain plate to a rotary hammer and expect it to survive a full workday? Because that is exactly what happens when you put a solid-state battery into a walking robot. The failure mode is not gradual aging. It is mechanical contact loss followed by abrupt functional failure. Beyond mechanical fragility lies a deeper industrial fear: random failure. Factories operate on OEE, overall equipment effectiveness, and OEE lives or dies by predictability. Liquid-based LFP batteries dominate industrial environments not because they are exciting, but because they are boring. They degrade linearly. Tesla's battery management system can forecast remaining life with less than 2% error. Maintenance can be scheduled. Lines keep running. Solid-state batteries, particularly high-energy designs using lithium metal anodes, do not fail quietly. They suffer from lithium dendrite propagation. Marketing claims that solid electrolytes block dendrites collapse under microscopic inspection. In practice, lithium filaments still penetrate grain boundaries and microcracks in ceramic separators at current densities as low as 1.0 milliamperes per square centimeter. Unlike liquid cells, this process does not announce itself. It ends with instantaneous internal short circuits, sudden, violent, and irreversible. Now scale this to reality. Imagine a fleet of 1,000 Optimus robots inside a gigafactory. If solid-state batteries exhibit a random failure rate of just 0.5% per month, 5 robots will die on the assembly line every month without warning. In an integrated automotive production line, where downtime costs approximately $22,000 per minute, this is operationally catastrophic. Which worker would you rather hire, one who gives 2 weeks' notice or one who collapses mid-shift without warning? Industry demands the former. Today, only liquid-based batteries can deliver that predictability. Public discourse around batteries suffers from a persistent misunderstanding: the confusion between energy density and power density. Media outlets obsess over 500 watts per kilogram, a metric that determines how long a robot can walk. What they ignore is specific power watts per kilogram, the metric that determines whether the robot can stand up after slipping. Optimus is a dynamic system. When it loses traction or lifts a 44-pound casting, Its actuators demand explosive current bursts with discharge rates exceeding 5 times the battery's nominal capacity per hour for mere milliseconds. This is precisely where solid-state chemistry fails. The interfacial resistance between solid electrodes and solid electrolytes is inherently high. Ionic transport across solid boundaries is slow, while liquid electrolytes routinely achieve 10 to 15 millisiemens per centimeter of ionic conductivity at room temperature. Many oxide-based solid electrolytes struggle to reach 1 millisiemens per centimeter. In practice, this means voltage sag. When Optimus demands torque, the solid-state battery cannot supply ions fast enough. Voltage drops below the inverter's cutoff threshold. The robot loses power mid-motion potentially while holding a load. Engineers attempt to compensate by heating solid-state packs to 60 degrees Celsius to improve conductivity. But this solution borders on absurdity. You add heaters, insulation, and thermal control systems to a robot that must remain lightweight. You burn energy simply to keep the battery warm enough to function. This parasitic load destroys the very efficiency gains solid-state batteries promise. In robotics, responsiveness beats capacity. A heavier battery that reacts instantly is superior to a lighter one that hesitates. Finally, we reach the only metric that truly matters to Elon Musk, the bill of materials. Optimus targets a price of $20,000. It is meant to be the Toyota Corolla of labor: cheap, ubiquitous, replaceable. The battery accounts for roughly a quarter of that cost. By 2026, structural LFP packs have fallen to around $85 per kilowatt-hours. For Tesla, a 3 kilowatt-hours pack costs approximately $255. This problem is solved. Now compare that with the manufacturing hell of solid-state batteries. Vacuum deposition, isostatic pressing. Exotic materials costs remain stubbornly high at $600 to $800 per kilowatt-hours. A 3 kilowatt-hour solid-state pack approaches $2,400. That is a 10-fold cost multiplier. Why would you equip a robot designed to replace low-cost labor with a luxury component that costs 10 times more than its alternative? It obliterates ROI. If a warehouse manager must pay $3,000 every few years to replace a battery instead of $300, the robot ceases to be economically viable. You do not install a Formula One engine in a delivery truck, and you do not install solid-state batteries in mass-market robots. The uncomfortable truth is this: solid-state batteries are a solution searching for a problem in humanoid robotics.